Hello everyone, I hope everybody is fine. This is a lecture about sinusoidal functions, trigonometric functions, and we want to do an application question. The Fundy Bay, located in New Brunswick, is said to have the highest tide in the world. And the time it takes between the high tide, which is 16 meters above the sea level, and the low tide, which is only 1.5 meters above sea level, is 6 hours and 13 minutes. So high tide 16 meters above the sea level, low tide 1.5 meters above the sea level, and the time in between the two tides is 2 hours and 13 minutes according to the given information. Now we want to know how long will it take for the first high tide to appear in a day. That's what we want to find out. So we are assuming that the nature of this high tide and low tide situation can be modeled with a sinusoidal function. That's first assumption. And also we assume that the time in the beginning of the day starts at equilibrium. So that's the assumption that we make. So we are dealing basically with a sine function because the function begins with equilibrium, just like a sine function starts from the axis of the curve. It starts from the middle. That is the equilibrium. Since it takes half the period to go from low tide to high tide, so this is the low tide and this is the high tide. So it takes half the period because you know that the length of one cycle is one whole period. So from the low tide to high tide, it's going to take half the period. Okay, so this whole thing is one period, and half of it is going to be 1/2 of a period. But the thing is that we know what the time is from low tide to high tide. So we're going to say the period, which is the length of one cycle, is 2 times the size of the time that it takes for the water level to go from low tide to high tide. So 2 times the 2 hours and 13 minutes time. If you double that time, that's going to be the period, of course. I said 2 hours. I think it was 6 hours. So I wrote this incorrectly. Let me fix this. It is actually 6 hours. It is not 2 hours. 6 hours and 13 minutes. So this is 6. So 6 hours would be 360 minutes, right? 360 plus 13 is going to be 373 minutes. So it's going to be 2 times 373 minutes, which is going to be 746 minutes. So now we know what the period of this sinusoidal function is. Here, the sinusoidal function is actually the height of the water level with respect to time. So if you think about it, if I just write y equals a sine of k times x minus d plus c, which is like general form of a sinusoidal function, now we can identify the value of k, to tell you the truth, because the period is 746, and we know that 2 pi over k is equal to the period. So if the period is 746 minutes, that means 2 pi over k is equal to that figure. And from there, if you cross multiply, 2 pi would be 746k. And if you divide both sides by 746k will be found. And if you simplify, it's going to be pi over 373. So this is how we calculate the value of k right there. Then we're going to go after finding the vertical shift, basically, this so-called C value. So this C value is right in between the maximum and minimum. So if this is maximum and this is minimum, that C value, that C level, is in between those two. In other words, we have to find the average according to the formulas we have studied in the past. So max plus min divided by 2, that's the average. So the maximum is 16 meters. That's the high tide. Minimum is 1.5. So you add them up and simply divide it by 2 to find the average. So it's going to be 8.75 meters. So you see how we are finding the values of AKDC values one after another using the given information in the problem. Now, for the D, because we assume that the time in the beginning of the day starts at equilibrium, so that means that the D, or the horizontal shift, doesn't exist and it's actually 0. So the value of D is 0. We have no reason to believe that there is any horizontal shift involved. And the value of A, or so-called amplitude, is going to be half of the distance between the maximum and minimum. So you know that amplitude is from the maximum point all the way down to the axis of the curve. So if you know the distance between max and mean, you just cut it in half. That's going to be the amplitude, logically speaking. We have talked about this in the past. So it's going to be max minus mean divided by 2. And max is 16, mean is 1.5. Subtract them, divided by 2. And this way, 7.25 meters is going to be the amplitude in this situation. So AKDC values are clearly found, and now we can plug them back in the equation, and we can claim that we came up with a sinusoidal function representing the height of the water in this high tide, low tide situation. So you don't mind if instead of letter X, I use letter T standing for time in minutes, and instead of letter Y, I use letter H in meters standing for the height. So the equation would be H equals 7.25, and then sine of pi t over 373, and I'm not going to write minus 0, it doesn't matter, plus 8.75. So this is the equation of the height of the water level with respect to time. And as you see, it is a sinusoidal function, okay, because high tide, low tide situation is a periodic phenomenon in real life. So just like a periodic function or sinusoidal function, the same trend happens over and over again. So now that we came up with the equation, we probably can find how long it will take for the first high tide to appear in a day. I can draw a brief graph of this function before I even answer the question. We know that the maximum value is 16 meters, so that this is the maximum line, and the minimum line is 1.5 meters. So these are the max line, which is 16 meters, and the minimum line, which is 1.5 meters. So whatever happens is happening in between these two. And 8.75 was that axis of the curve, basically. So if I can write the equation as h equals 8.75, or y equals 8.75, and this would be like h equals 16. If I label the equation of line, this could be also h equals 1.5 if you want to label. So these are the three lines that make the maximum line, axis of the curve, and the minimum line. And we know that we start on the vertical axis right there because of the assumption that we made before. And we do know that the period is 746 minutes. We just calculated it earlier. So 746 would be somewhere here. That is one cycle. And if you double that, it's going to be 1,492. That would be the end of the second cycle. So basically, beginning of the cycle, end of the cycle is very clear because we do have the length of the period. And half of the period is going to be 373 minutes. That's going to be the middle of the graph, the midpoint, and then we have the quarter points in between those two, which is happening here and here. This is just a sketch. So the graph is going to look like something like this. If we try to draw this meticulously, it's going to be a graph like this. Now, the second cycle is a repetition of the first cycle, and it looks like the same graph, but I'm going to try to draw the second cycle of it. So this is maybe happening on the next day or next time that the tide is happening. So the water level continuously changes. It goes up and down, up and down. We end up with like a high tide of 16 meters above sea level, and then we end up with low tide, and so on and so forth. The same phenomenon keeps repeating periodically every 746 minutes. Okay, so now we are going to find how long it will take for the first high tide to appear in a day. That's what we need to find out. Okay, so how can we do that? From the lowest point to the highest point, we know how long it takes. So the first time that we end up with the high tide, this is the first time, the height here is actually 16 meters. So what we can do, we can plug in 16 for the height, okay, because that's the first time that the high tide happens, and then we can solve the equation for time t. So 7.25 sine of pi t over 373, okay, plus 8.75. So this is the equation we need to solve. The height is 16 meters, and we need to solve for time t. So in order to do this, obviously, we're going to move 8.75 to the other side. So minus 8.75, 7.25 sine of pi t. And from there, we end up with 7.25 on the left. So if you divide both sides by 7.25, you end up with just sine of pi t over 373 equals to 1. And obviously, if you want to find the angle, which is pi t over 373, you should take the inverse sine of 1. But inverse sine of 1, on your calculator, you may see 90 degrees. But here we don't deal with degrees. Everything is in radian. Therefore, you should not write 90 degrees. Okay, you should write pi over 2 radian, which is the equivalent of 90 degrees. So inverse sine of 1/2 here is going to be pi over 2 radian, okay, not 90 degrees. So I'm going to say pi over 2 equals pi t over 373. And now I need to solve for time t, which gives me 186.5. So 186.5, and that is the time measured in seconds. So this is the time required to reach the first maximum, basically. So it tells me that from the equilibrium line up to the first max, which is like this distance here, this horizontal distance, apparently is 186.5 seconds. And if you double that, I bet it is going to be 373. I have a calculator here. So 186.5, if you double that, it's exactly 373. So how long will it take for the first high tide to appear in a day? The answer is it's going to take 186.5, not seconds. Why did I write seconds? I just noticed that the unit is minutes, it's not seconds. So 186.5 minutes is going to be the time it's going to take to reach the first high tide in the day. I hope you understood how we did the question. The most important part is to be able to find AKDC values using the formulas we have studied in the past. For example, C equals n plus m over 2. and minus m divided by 2 is a, 2 pi over k is the period. All these formulas we have learned in the past, we use them to come up with the equation of the sinusoidal function. And then after that, if you know the height, you can find the time. And if you have the time, you can find the height easily from the equation. Perhaps we're going to work on more word problems in future. Thank you.